Hello, statistical scholars. Today I'm going to talk to you a little bit about one of my favorite topics in statistics, and that's hypothesis testing. So, hypothesis testing is the idea that we have some statement or claim regarding the population that we would like to test using some sort of statistics. So, to see how likelihood that hypothesis is true. So more often than not, this is going to be something where you have historical data on something and you want to ask, hey, is that proportion still true? Is that mean still true? Because it used to be the fact that we could easily determine if something was still viable by just going and grabbing a census. But if you're in between the census years and you wanted to know some information, you might ask yourself, oh, does my current population still behave that way? In which case you'd want to perform a hypothesis test. So the idea is that this is very formulatic and has a lot of the same steps. So we'll have some sort of claim. We'll have information or sample data that we've collected, and then we use that data to either really test the claim to see if it's valid. So we're going to assume it's true and then move on and see if the evidence points towards it or not. So the idea is that in inferential statistics, we want to ask ourselves, is the sample I gathered or the evidence I gathered really rare or kind of plausible if what I'm assuming for the claim is true? So is it likely that it occurred by chance? How probable is it? Or is it just so unlikely that it could not have possibly occurred by chance? When it's not possible to have occurred by chance, so if it's a really rare event, we call that significant evidence. So now the word significant has a specific statistical meaning for you, which is kind of fun. So let's look at this first example. So according to the National Center for Chronic Disease and Prevention, 73.8% of females between the ages of 16 and 29 exercise. Jill believes that more women between the ages of 18 and 29 are now exercising, so she obtains a sample of 1,000 women and finds that 750 of them are exercising. Is this evidence that the percent of women between the ages of 18 and 29 are exercising has increased? If Jill's sample had been only 920 women, exercising. So the idea is that if your proposed value that you're testing is 73.8%, and she gets 708, we should expect 738 of them are going to be exercising. Similar proportions is all we're doing here. So the idea is if you get 750, well, that's not too far from 738, aka the 75% she's getting, is pretty close to 73.8. It's probably not far enough to be statistically significant. However, when we look at 920 out of 1,000, that's 92%. That might be statistically far enough from 738 to probably not be caused by chance. How do we judge whether or not it's significant or not being caused by chance? Well, we ask how likely is that sample compared to what we should expect. So we want to ask ourselves, how far off is this proportion from that proportion in a way that is statistically significant? Is it that much? So what we want to figure out is looking at that 920, if it were true that that was the sample amount, is that far enough away to be strange? So usually our way of discovering that is using the sampling distribution and using z-scores. Remember, z-scores are used to tell how many standard deviations away you are from the mean, and if you're more than 3, then that's pretty significant. So that's what we're going to be doing with this. So it's likely that this 738 is not the correct proportion if we got 920 out of the 1,000 women exercising. So we want to ask ourselves, that second idea of, okay, it's actually increased, or is it higher? She thinks it's higher. Seems to be more correct. So the idea is I'll have something that I want to test. I'll have an inkling for what I think it is, and I want to test these against each other. So that's the whole basis of hypothesis testing. So the null hypothesis is going to be a statement that we are going to be checking. We're going to assume that this one is true and then gather evidence either for or against it. And that's going to be our second option. So the null hypothesis is assumed true until evidence indicates otherwise. That's why we need evidence. Now, the alternative is also called the research hypothesis because it's the one that you either suspect is true or possibly could be what you think the evidence is pointing towards, but you may or may not have evidence yet that that is true. So the null has to be something that you're testing, and it's going to be something you assume it's true. And since it's like that, it has to be a statement about equality, because you can't test less thans or greater thans on a normal distribution, because you're assuming a certain proportion amount is going to end up being your mean, as we'll see. and that's why this works the way it does. So the alternative will either contain, a less than, or greater than, or less than or equal to, or sorry, not less than or equal to, or a not equal to. You can also have equal tos on the less than's, greater than. It doesn't make a difference. So we start by assuming this is true. That's why it's called a null. Null stands for starting or initial, for those of you who've had physics before. And so this is our starting truth, and then we're going to do some work to see, is it true or not? If our evidence points otherwise, we might be like, I don't think so. It looks like my research is, pointing towards that. So if the evidence we gather points strongly against the null, we reject it, and then we sort of say that it appears that this is the other option, because that's where our evidence will point towards. And we'll see how this works. So hypothesis testing does not lead to proof. You never prove truth. You mainly have evidence either supports or doesn't support, so be careful about this. Anyone who claims that they can prove truth or falsehood using data is completely lying to you. It's, yeah. You can only see patterns and make observations, and test things and show that they're extremely likely, and that's about it. You can only make statements about probability. So here are some claims that are regarding characteristics of populations that we can look at. Yay! According to a Gallup poll released in 1995, 74% of Americans men felt more aggressive than women. Researchers claim that the percentage of Americans that feel this way is different today. A claim regarding the population. So they think it's different now. So that's something you could test. A packaging of a light bulb states that the bulb would last 500 hours under normal use. A consumer advocate group would like to know if the mean lifetime of a bulb is less than 500 hours, aka we don't think they're telling the truth. We think it's actually smaller. And so this is something against a population mean that we could test. So for number one, the null hypothesis we'd be looking at is our proportion is 74%, because that's what we claim. An alternative would be a not equal to. So how you recognize a not equal to is when you see the word different. That's a big indicator that it's going to be a not equal to, or differs from, or is not the same. And then for statement number two, if the manufacturing claim about the bulb, the null would be that it's equal to 500 for the mean. And then, our alternative would be that the mean is actually smaller than 500, because we think it's actually less than 500. So look out for less than, greater than, more than, and all of those lovely keywords that indicate that we should be using an inequality instead of a not equality or an equality. So remember, your nulls are always statements about equality, because that actually we can test. So the null idea is going to set up your sampling distribution as like, oh, well, that's the mean, and oh, that's the mean of my distribution, the actual p. So these are giving this a distribution to work off of, a center, and then we'll form the standard deviation or standard error off of that, depending on what we got, and then use that evidence I gather, which we haven't done here, we've just made claims, to either support or deny these claims. And we'll see how the alternative plays into, well, how do I decide what my evidence looks like? So in this class, we'll look at three ways to set up the alternative hypothesis. There's the two-tailed tests, and that's when you have a not equal to. And then there's something called the left-tailed test, which is the less than, and then the right-tailed test, which is a greater than. So bigger than that value, less than the value, or not equal to. So these collectively are called the one-tailed test. The left and the right together are called the one-tailed tests, because there are two of them, and they are different. Actually, really, all three of these are different. Anyway, so for each of the following claims, determine the null and alternative hypothesis. State whether the test is two-tailed, left-tailed, or right-tailed. The proportion of divers who admit to running drivers, not divers. I write this, that's horrible, who run red lights is greater than 0.05. So this greater than, remember, you can only do equal signs for your null. So our null is going to be equal to 0.05. And then our alternative, the one we suspect our research will support, the one we're looking to research, is going to be that greater than. So this is going to be a right-tailed test, because I'm going to be shading to the right of 0.05. Oh no, I'm giving away where this is going already. The mean amount of Coke cans is less than 12. The mean amount of Coke in cans is less than 12 ounces. This is a very typical product testing idea, and that's did my machine fill it enough? And so again, remember our null has to be an equal to, and then since I think it's filling less, I would say less than indicates 12, so that would be our alternative, which we would indicate a left test, because I'm looking at stuff that are to the left of 12. That's another way to think about this. Okay. Medco Pharmaceutical Company has developed a new antibiotic for children. Among the competing antibiotics, 2% of children who take a drug experience headaches as a side effect. Oh no. The research for the FDA wishes to claim the percentage of children taking the new antibiotic who experience headaches is actually more than 5%. So again, that more than indicates what our alternative is going to be. We think it's going to be a greater than. Again, so I'm looking at values that are greater than 0.02. this will be a right-tailed test because I'm looking at things to the right of 0.02, and my assumed null is going to be 0.02. So there you go. The Blue Book value for a used Chevrolet Corvette is $37,500, and John wishes to test the claim that the mean price of a 3-year-old Chevy Corvette in Detroit metropolitan area is actually different. So this is interesting because Blue Book is from across the country, and then in a specific area, it might be different because you're looking at a different area. So he just thinks it's different. There's that different word, so that's probably going to be a not equal to test. So two-tailed. Watch out for differences, yo. Anyway. So when it comes to stating the conclusion of a hypothesis test, we always, test the null. We're just testing the null. We draw our conclusions in the following way. We either say, well, this isn't really a conclusion. This is sort of the decision you make. You either reject the null because your evidence seems to point that it's not true, and then we can also fail to reject the null, which means that I don't really have evidence this is true, but I don't have evidence that it's not true. And this is sort of like the boy who cried wolf scenario. Sometimes there's a wolf, sometimes there's not. But you, when you are running to go see what he's calling out about, don't know if there's a wolf or not. You just know that you need to show up because scary things happen. Or you could choose to not show up, in which case there's no wolf. I'll get into that in a minute when I talk about errors, because that's sort of where I'm going with this. And another way you can think about this is the jury reference, and this is what your book uses. The idea is that if you're on trial for, doing something naughty, which you may or may not have done, there's no way for the jury to decide whether or not you are actually innocent. They declare you are either guilty or not guilty. They don't declare you innocent. Only you know if you're innocent or not. So be careful. It's the same idea. Only the data shall know if it is something that is true or not. You simply declare whether or not your evidence points towards it or points against it. So, so again, not acceptance, just rejection, or not fail to rejection. This is one of those cases where rejection is more preferable to acceptance, which is rather unusual, I would say, but that's where we're at, yo. When a null hypothesis is not rejected, we say that there's not sufficient evidence to support this claim. That is, the sample data supports the null hypothesis. It indicates that the null hypothesis might be true, but we can never really say if the null is true. So don't say it is true. Be careful. So we will use sample data to determine whether or not to reject the null hypothesis. Because we are using sample data, there's always the possibility of making an incorrect decision because different samples yield to different results. I am getting a knock on my door. Hold on. So we will be using sample data to determine whether or not to reject the null hypothesis. Because we're using sample data, there's always the possibility that we make an incorrect decision. I am repeating myself. Oof. That's what I get for taking a break. Anyway, so these 4 things are going to be the crux of what could possibly happen. So look down at this little diagram I've given you below, not before. we reject the null hypothesis when the alternative is true. So we made the correct decision. We do not reject the null hypothesis when the hypothesis is true. This is also a good decision, so that's these good decision corners. So it turned out to be true in reality, and we didn't reject it. The alternative turned out to be true in reality, and we rejected the null, so we made the right decision. The other problem is that you could have the opposite happen. You could end up with what we call a type 1 error, which is where you reject the null hypothesis when the null hypothesis was actually true. Oh no! Darn it! This is what we call a false negative. It shouldn't have been rejected, but we did it anyway. And if we do not reject the null hypothesis when the alternative is actually true, aka we made the wrong decision, we kept the null when we shouldn't have, we've made what's called a type 2 error. Oh no! This is also something bad. And this is called a false positive. So if you've ever had to do any medical testing in your day, say you were trying to get tested for like strep throat, they want to avoid these in medical testing because they don't want to tell you that there's certain errors we want to avoid. Like, hey, let's see if you have strep throat. So when we look at the conclusion over here, that's the result of our test. And up here would be our reality. So let's say, you actually have strep, and then the test said, oh, you do. Good job. And down here it would be, oh, you actually have strep, but the test says, nope, you don't have strep. Oh no, no medical intervention. That would be the type of thing we'd like to avoid. Here's the other option. You don't have strep. Oh no, my test indicates that you do have strep, so we're going to give you medical treatment that you don't actually need. And then down here below it would be, oh, you don't have strep, and it turns out that my test said you didn't either. So basically the medical community and statisticians agree that the type 1 error is the one we're going to try to avoid the most. It's the one that's, the one we don't want to have happen. The case where people who actually need treatment don't get it. We're okay with extrally treating people who don't actually end up being sick. However, if you're somebody who's been diagnosed with something a little more negative and you actually find out later that you didn't have it, you might be a little more miffed. But we don't want to accidentally undertreat people, so the type 1 error is usually generally considered to be worse. So this is why I said that we are looking at what we call alpha, which is what we call the level of significance, and it's the probability that you make a type 1 error. That's the one we're mainly concerned with. So when looking at the value for alpha, we want to make sure that we're looking at those consequences, and we don't want to make that error, so we want to keep that small in general because errors are bad. So we usually use a level of significance or an alpha of around 0.05. This is the one used by the American Society of Statisticians and generally agreed upon in the statistical community as the standard. However, I have seen ones with 10, 15, or even 1% as the level of significance. When in doubt, if you're not sure what level of significance you should be using, we're going to use 5%. So if you're ever doing a problem and it doesn't say, you should be using 5. Yay! Okay, so here's how we test claims about a population mean. So to test a claim regarding a population mean, assuming the population standard deviation is known, there are 2 requirements to be satisfied. It's a simple random sample, and the population from which it was obtained is normally distributed or the sample size is large enough, aka bigger than 30. These should look fairly familiar to the confidence interval requirements because they're exactly the same. It's, hey, I want to use the sampling distribution. And we're going to be using what's called the p-value method, where we compare the probability of getting that sample or worse to the level of significance or alpha. So we're going to test the claim on the population parameter in the following method. So what we're going to do is we're going to begin testing the null hypothesis, assuming that it's true. So that's going to be the mean of our deviation, of our, come on words, where's the word I'm looking for? That's going to be the mean of our distribution. So thinking like, here's my null value, either my p or my x bar. Same thing here, center of the distribution. And that's why we do this, so we have a distribution to work with. So as we gather the sample data, our p-value is the probability the sample will result in that sample or a more extreme case. So the idea is that p-values are going to be probabilities. So low probabilities are going to be unlikely events. So if our null is true, should I be really getting an unlikely event or a highly unlikely event my first try with my first sample that I grab? Probably not. And that's going to be evidence against null. However, if the p-value I get is really high, then I'm going to be like, hey, this seems pretty likely if h naught is, true. So I would fail to reject it, and the test is a little inconclusive in that case. So the idea is that we're going to gather evidence. So we're going to do this by formulating test statistics or coming up with z-scores, and then looking at the probability of getting that z-score or worse. So the critical region that we're going to look at is the set of all values that are the test statistic or worse according to the opposite of the null hypothesis, so our rejection area or our alternative hypothesis. So our significance level alpha is going to be our cutoff for when we think something is significant. So whether or not the null is going to actually be true. So here's how we think about this. So we got our, two-tailed test. I think I'm actually going to start with the right-tailed test. So here's the idea. I want to see what the probability is that I get my test statistic, which is my z-score right here that I get from my sample, or something that's greater. Remember, right shade to the right, that way, critical region. So this critical region, the probability of that region of getting that sample or worse is larger than what I expect to be significant, then it's significant evidence, for the null. Or, yeah, for the null because it's large and very common. However, if I get this and it's small, then I've got something that's very uncommon, and then it would be significance evidence against the null hypothesis. Because if the null were true, should I really be getting something tiny? Now, remember with a two-tailed test, it's a difference, so it could be greater, it could be less than. So we need 2 of them. So basically what we usually do is we calculate one region, and then note that since this distribution is going to be symmetric, we can just double it and come up with the other one. So you fail if you're either too large and therefore significant in probability, or too small and therefore significant probability, because remember this is a difference test. All right. The same thing is true for the left-tailed test. So this is probability or less. So this is, because our alternative hypothesis is a less than. So I look at the critical value I get from taking my sample minus my mean divided by my standard deviation for this sampling distribution and get that region. So again, the idea is I reject if my p-value is small, aka it's significantly small. It's smaller than alpha, our level of when things become significant. We fail to reject if p-value is large, so it's a common, it's a likely sample to get. And therefore is bigger than our significance level, and we don't reject our H naught. Whee! So again, here are your 6 steps to approaching a claim. Yay! We use 6 steps when it comes to doing a p-value hypothesis test. There are other ways to do this, but we're going to do the p-value one. If you go on to take stats 2, you'll see some other ones. So first we state our claim, we determine our null and alternative hypothesis, we determine our significance level, which is usually given to us, and make sure we're aware of what the rejection rule is. Based on the given data, we've used the appropriate statistical test, either the one proportion, the one sample z, or the one sample t. We're going to see that this follows exactly like the confidence interval tests and uses the exact same mini-tab screening as we've seen before. So it's not going to be too surprising what happens here. And we use the exact same determiners to decide if we're going to use the one sample T or the one sample Z. So Z or T, use the same ideas. Woohoo! We state our initial conclusion. This is usually called the decision, not the conclusion, but our book uses conclusion, so I'm going to call it conclusion. We either reject the null hypothesis or we fail to reject it. And then the last thing you should do is you should state your conclusion in non-technical terms. The reason we do this is because usually when you're reporting statistics to people, they're not statisticians. They really need a logical reason to do this. So when I look at conclusions, I look at the following. Does it actually answer the question that we started with? Is it actually using statements about the actual data that we have, not just saying, null hypothesis was false and I failed to reject it, blah, 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 blah. No, you tell me things like, hey, it appears our data is pointing towards it being actually a fewer number of women who exercise rather than the claimed proportion of 78%. That's much more natural sounding. And the last thing I look for is it provides some reasoning or evidence behind that. So the reason I made to decide this is, because my p-value was really, really small. Or I decided it at a significance level of 5%. I'm stating at what point did I make this decision. So let's look at a completely worked out example, which is what this is here. And I've got the mini tab written out here behind this, but I'm also going to do a video on just doing this in Minitab and in Minitab Express. But I'm going to mention some of these things as we go through. So, first up, hey, suppose a consumer claims a manufacturer of potato chips is underfilling its bags. Oh no, all that air. For, you know why the air's there? The air is there so that when you're shipping them, you don't crush all the chips that are in there. And you don't end up with just a bag full of crumbs at the bottom. So don't complain. Anyway, so the bag states the weight is about 12.5 ounces. The hypothesis test, we assume that the manufacturer is not guilty, which means we assume that the population contents, and I'm going to have to pause again. All right, so we're looking for evidence to support the claim that the manufacturer is underfilling the bags, i.e. the mean weight is actually smaller than 12.5 ounces. To test this claim, we have the following hypotheses, which you can read right there. Clearly, this is a left-tailed test, so I'm looking at things that are less than. So the consumer advocacy gathers evidence by obtaining a simple random sample of size 36 and weighing the contents and finds a sample mean of 12.45 ounces. Now, you might look at this and say, oh, it's smaller, done. Is it significantly smaller? Is it statistically significant? Or is it just smaller and it's caused by random chance and not the fact that it's actually smaller? Only one way to find out, and that's to use a statistical test. So using the p-value approach, we are going to test the consumer's claim using 0.1 significance level, so 10% level. So we take our sample of size 36. We know from the central limit theorem that the distribution of the sample means is approximately normal. So since it's a sample, we know it looks normal. We know that its mean will be the same, so it's got to be the same as our claim of 12.5. We assume that the population standard deviation is known to be 2 ounces, this has to have been given to you. If it's not, then we better be doing a t-test. So then we know our standard deviation for the sample means is, the 0.112 divided by the square root of 36, so about 0.02 ounces. And then we're going to use the p-value approach. So we need to compute how likely it is that we get a sample mean of 12.45 or something worse, which would be something less, since we're looking for less than, aka left tail, than the 12.5 ounces. If the sample, and that'll be our evidence against the null. If the sample mean of 12.45 is, or something smaller, is not unusual, then we don't really have evidence. So we compute the probability and obtain the obtained sample mean of 12.45 or less from the population using 12.5 as our assumed mean from the null hypothesis, and we use the normal distribution model. So we're looking for the probability that my sample is smaller than 12.45. So it's that value or worse, where worse is coming from the alternative. And so we use Minitab, and that's going to come up with 0.006. And since our p-value is smaller than our alpha, we're going to reject the null hypothesis, and that means there's sufficient evidence to support the claim that the mean weight is actually less than 12.4 ounces. That is, the manufacturer is actually underfilling the bags of chips. So in Minitab, you do that using the one sample z for means. This is the exact same thing you use for the confidence intervals. The only difference is that you need to check this perform hypothesis test box and give it what you're comparing it to. So notice that this is coming from the assumption from your null hypothesis. It's important you write your null hypothesis first and your alternative before you start getting into Minitab, because you also have to tell it what your alternative was. So notice hypothesis means 12.5. So down here when it says hypothesis mean, it's referring to this value you gave it. So you're testing, hey, is the mean less than the 12.5 I put in there for that value? So this is forming your alternative hypothesis right here at this line. Lastly, you should give this a confidence level. So remember, confidence level, that's how confident you are for a confidence interval. Hey, but it's also related to, hypothesis testing, because it's actually 1 minus alpha, the significance level. So since our significance level was actually 1%, what I really should have put in here is 90%, since it's this one. But as you can clearly see, I took a screenshot and then realized I had this in here wrong. Haha! Sorry, I'm lazy and I didn't fix it. So it actually doesn't matter so much what you put in here. It's just going to produce a confidence interval based on that, which we're not even going to need because all we care about is p. So we look down here and we notice that our p-value is super small, which is evidence that the null doesn't appear to be true. The other thing to watch for is up here, it's going to list for you the null and alternative hypothesis. So if you're worried about getting this less than or greater than correct or incorrect, as long as you write your alternative first and then compare it to this output, notice how it says mu less than 12.5. Hey, it's going to tell you if you got the right one in there, if you're worried that you're going to choose the wrong setting in there, which is kind of nice. And it also lists that assumed standard deviation because we're using the z, not the t. So that's what this looks like. And all you really need to pay attention to is this p-value. And notice that since that p-value is smaller than the 10% we picked as our significance level, that's how we knew we're going to reject the null hypothesis and actually say that the evidence is showing that it looks like it's going to be less. Alrighty. So the thing is if you're dealing with a population mean that you don't know sigma, or you have a small sample size, you're going to be using t. Woohoo! So, simple random sample needs to be larger than 30, and that's how we look. We're just going to be using a different test statistic. Again, we're going to be using Minitab to calculate the p-value. It's just we'll be using one sample t instead. And then lastly, if you're dealing with a population proportion, we are simply doing the same thing, only I'm using a one proportion test, and its test statistic is a little bit different, but it still looks the same. The estimate minus the population proportion or parameter divided by the sampling distribution standard deviation. So as you look at this, I'm going to do some more examples using these on our example test sheet, or example sheet, sorry, for this week. But as you look at these different population proportions and means, be aware that there is actually 3 tests we have, 2 for means and 1 for proportions. And that's about it. Alrighty. Happy last week. Bye.